Hi, everybody. I'm Paul Luse, active SPDK contributor, along here with my partner in crime, Ben Walker, SPDK maintainer. Okay, here we're going to talk about a bunch of cool stuff. We're going to talk about what makes software cloud native, or more specifically, what makes SPDK software cloud native. We're going to take a look at who's using SPDK in the cloud, including integrations and some community members that you may or may not know about. So hopefully there'll be a surprise on there for at least a few people. And then Ben's going to cover what SPDK has been doing over the last couple of years that makes it quite a bit more cloud native friendly for storage applications integrating SPDK. And then finally, a long list of fun to do items of things that we can still do better. Okay, so what makes software cloud native? Before I jump into this, I figured it'd probably be good just to level set really quick on what we mean by cloud native. And probably the best way to do that is to describe what we mean by not being cloud native. So not cloud native is really the traditional old monolithic application style. We're going to build an application based on a bunch of libraries. It's going to be just this single thing. And if you need to scale it, you either instantiate another instance, or you go back and you rebuild the application, you make some changes, and you redeploy it. In cloud native, you don't have to do that. Besides a ton of other benefits, you really would describe the application as a set of loosely coupled microservices that are managed by an orchestration engine, something like Kubernetes, where each one of those microservices has a specific role that it does within the application and can be scaled independently. And in addition to that, all of those microservices can be load balanced and moved wherever they need to be moved within the cluster or even off the cluster to make sure that you deliver consistent performance. So that's kind of what we mean by cloud native in a nutshell. Obviously, there's a lot more to it than that, but figured that'd be a good setup before we get on to the next slide. Okay, what makes software cloud native? If you have ever Googled what makes software cloud native, this is likely not the list you're going to find. This is really a list really through the SPDK lens. And if you really pay close attention, you're going to hear Ben touch on each one of these items as we move forward. This is almost a list of what has SPDK done that isn't so cloud native friendly. So starting with the top, you must be able to run without assumptions about hardware, right? So just as I described, right, a microservice or an application can be moved at will by the orchestration engine to any piece of hardware or any node that it needs to be moved to, any hardware that needs to be moved to. Now there are of course restrictions and ways that you can get around this, but we want to make sure that that the SPDK building blocks don't just make assumptions that there's underlying hardware there and then end up exploding if it's not there. We want to be managed using HTTP REST endpoints, right? This is just the standard way of communicating. And then here's the fun one, right? Can't be polling. How can we say that as the SPDK community, right? Polling has been a mainstay of SPDK since its inception. But as you can imagine, right, if you were sitting in a cloud where applications can be moved to load balance CPU usage, the last thing you want to do is be the guy that is hogging up CPU usage, even when you're actually not using the CPU. So we don't want to be a noisy neighbor. We want to do something about that. And then no extra privileges, right? That just makes it more difficult for the IT administrator. It makes it more difficult to move services around. And of course, with SPDK, we need huge pages along with a couple other things. So that's another challenge for us. And we really don't want a ton of dependencies on Linux specific kernels, right? For all the same reasons that I've been talking about before, you can be moved around. You really don't want to make assumptions about what the underlying operating system is or what version it is. That just makes you a much less flexible application for being moved. All right, so now we're going to talk about who uses SPDK in the cloud. And we're going to start with sort of a laundry list of integrations. And I'm not going to go through and read all these for you. You can certainly read them on your own, but you can see we've got sort of a variety here: orchestrations, databases, software-defined storage, virtualization, kind of over the map. But I'll pick a few just to have fun with them. All right, Kubernetes, got to call that one out since this is a talk about cloud native. With SPDK, we've got the NVMe Fabrics and iSCSI CSI drivers, thanks to Yibo. And if you stick around for the demos at the end of the summit, Monica's going to be doing a demo, a live walkthrough of deploying the CSI drivers. If you want to see that in action, be sure to catch that. Maya Data is a really big name. They've been in the SPDK community for a while now. A lot of you folks probably know them. I've got a whole slide on them coming up next, so I won't talk any more about them. Here's one that, unless you've been really paying close attention on Slack, you might not know that Portworx is in the process of integrating SPDK into their cloud native solution. I don't believe they've publicly announced it, but they've publicly talked about it on Slack. So that's pretty cool. That should be coming, hopefully soon. And we'll see a couple of the, with Maya Data and Portworx, two of the sort of biggest, most popular names in cloud native storage solutions leveraging SPDK, which, we should all feel really good about that. Okay, so now let's take a closer look at Maya Data. They've got just so many cool quotes on their website. I had to clip a few in and throw a slide on these, right? They just attribute SPDK all over the place. It's awesome. They're achieving absolutely incredible performance with their Mayastore product. I actually had an opportunity to play with Mayastore a couple months ago, and I was pretty impressed. Next up is the Windows Performance Development Kit. If you've seen any of these discussions with Nick Connolly on Slack or seen the patches coming in, if you need to run your SPDK application on Windows, Maya Data has made it possible, and you can go to this URL for more information about the WPDK. And then finally, this was just out of a blog. I just loved the title. It was awesome. The Mayastore Data Plane, or How I Stopped Worrying and Learned to Love SPDK. So Maya Data, we love you too. And with that, I'm going to turn it over to Ben to go through the what have we done and what do we have to do.
Thanks, Paul. Yeah, I'm going to cover things SPDK has already done to make us more friendly to cloud and deployments, and then things that we can do in the future, which is the excited part. So the first and most obvious thing is we entirely changed the way SPDK is configured. This took years if you've been watching us. Initially, SPDK was configured with a static INI file, and you would provide this file when you started up the software, and it would set everything up and it would run. We've since switched to a mode where the application starts in bare bones mode, and everything is then configured by sending JSON-RPCs over a Unix domain socket. And you can dynamically configure it. You can add and remove things, change all the settings around as you go, and you don't have to restart the application every time. This may not seem like a cloud native move, but it certainly is a key component of our cloud native strategy. We need to be configured like a cloud native service. And so in one of our recent releases, we entirely eliminated support for the INI files finally after years. You cannot provide INI files to configure SPDK anymore at all. And then I also want to point out that SPDK does not provide an HTTP endpoint to any of our targets, but it should be relatively simple to proxy a REST interface to these SPDK JSON-RPC calls via a Unix domain socket using whatever HTTP infrastructure or framework that your company uses. Another big one that I have talked about at past SPDK summits is a transition away from one thread per core pinned with a reactor processing events to a lightweight threading model where we have a set of lightweight threads mapped M-to-N onto P threads. Those P threads may be pinned to cores, but don't have to be. And we have entirely embraced this model. We've switched over. The hardest things that initially there were data structures where the index was the CPU core, and it would look up based on what core you're on into the data structure to figure out context. And all of that has been eliminated and is gone. You don't have to pin threads at all. SPDK can add or remove both P threads and lightweight threads at runtime, and completely shift around. So in the version of SPDK today, at least the LTS release, the lightweight threads are assigned to the P threads as they're created round robin to try to get them distributed. But there are additional things coming or in the latest release to make that even more flexible, which I'll talk about now. So the lightweight threads now can be moved at runtime, not just as they're created, between the P threads. And we can shift around these lightweight threads so that, if we determine that one thread is enough, one P thread is enough, we can shift all the lightweight threads to that P thread, then put the other P threads, which now have no lightweight threads scheduled on them, entirely to sleep and save the power. So we're still polling on one thread as of our latest LTS release, but we can dynamically scale up to the maximum number of threads and back down to one as needed. And this largely works without any performance overhead that we measure. There's no big ramp up time or anything like that. It goes fairly seamlessly up and down and saves the power. So there's also ongoing work to enable interrupt mode, which I'll talk about in the future work section. This would allow even that one thread that is still polling with all the lightweight threads on it to, if it decides that every lightweight thread happens to be itself idle, we can drop to full interrupt mode, and that is complete idle, and we're woken up in response to events only. So we don't plan to operate in interrupt mode while we're running. This is for periods of idleness, and then we'll burst back up to pull mode as normal when it is running. So the most important things these do in relation to the cloud is that they allow for flexible threading models that scale up and down CPUs and enable things like running on burstable instances that a lot of the cloud providers have. These sort of instances, if you're below a certain amount of CPU use, you accrue credits, and if you're above a certain amount of CPU use, you spend your credits. And if you run out of credits, you get throttled or charged more, depending on how they're set up. So these sort of instances, if your workload is bursty, can save you a lot of money to be able to run on them. And you really, before, couldn't run SPDK on these instances, or it wasn't feasible to, because we were just polling on 100% on everything, even when you're idle. And now we believe you could run on these sort of instances and actually benefit. All right, another thing we've done, which is another one of those sneaky things that you don't necessarily think of as important for running in the cloud, but actually really is in practice, is we made a bunch of build system improvements over the last couple of years. Most notably, or one of the important things is we've allowed you to now specify the target architecture when you're compiling, and that's more granular than just x86, 64, ARM, or Power, which we've supported for a while, but which generation of that architecture. You can select Skylake or Broadwell or something like that. This is important because when you run in the cloud, you don't know what system you're going to end up running on. You build it on one system, and then you deploy it to a cluster, and you don't know what that server is necessarily. Like maybe you know that it's an x86 64 server, but you don't know what generation it is or what instructions specifically are available. And so this allows you to target the lowest common denominator, basically. And then you can guarantee that you can run anywhere. We've also done a lot of work, Jim Harris especially did a ton of work here to make our shared library dependencies discoverable from the libraries themselves using package config. So you can run package config against any of the SPDK libraries, and they'll report what other libraries they depend on. So you can discover the dependency chain on a system as you're deployed. We also do shared library builds with strict, tested, checked ABI rules and ABI versioning. And so you can tell when you run on a system, if you want to dynamically load SPDK into your application, you can tell for any given library what ABI version that library has and if you're compatible with it, which is important because sometimes you get deployed onto systems and you don't necessarily know what is there. And then, of course, we've done this for a long time, but we have fairly strict API versioning checks as well, to try to avoid breaking the API for critical components that we've deemed are stable. And then here's an old one, but we continue to support it and think it's critically important that remains important, or it becomes even more important in the cloud. You can still run SPDK as an unprivileged user. You do not need root. We do not recommend you run as root. You do have to set up the permissions ahead of time, which is mostly configuring your IOMMU with the appropriate groups and granting permission to create huge pages to the user you want to run as. I would like to note that using a virtualized IOMMU does work. So even in a virtual machine where you have a vIOMMU, you don't have to run as root. You can run as root, especially if your virtual machine is already protected, by a physical IOMMU. But these vIOMMUs are not always available in the cloud, and sometimes they do have, performance overhead. So I just wanted to point out that it does work, especially if it's hardware accelerated. It may be a good option. Okay, and now getting into the most exciting part. What else can SPDK do going forward? So right now we have some challenges with binary portability. I touched on this with the build system, and I mentioned that you can solve this by building for the lowest common denominator, and that's great. If you target an older architecture, it solves the problem. They're portable, but you also don't get the benefit of new CPU instructions. So, conversely, if you were to build the binary targeting the very latest architecture that you may encounter, your binaries are no longer portable, but you do get all the new cool instructions. So you're kind of stuck there. And really what we want is the best of both worlds. And so the solution for SPDK is that we need to do runtime detection instead of compile time targeting. And we've begun the process of this to some extent. GCC, one of our compilers that we support, has a feature called multifunction versioning. It's very slick. You basically get to tag certain functions that use intrinsics or drop to assembly, and you tag them and say, I want a version of this compiled for Core i7. I want a version compiled for a processor that has this this feature set, etc. And it will compile a version of each into your binary, and then at startup time, it will query the CPU ID for each for your CPU, and it will patch itself with the right version of the function for that architecture. So you get the best of both worlds. So as I mentioned earlier, our build system now lets you target the oldest system that you may encounter so that you can guarantee that you run. But that precludes you from accessing or using any of the new CPU features that may be on some of the newer platforms in a particular cluster. Conversely, if you were to choose the very latest platform in the cluster, that would use all the new cool CPU features that you may encounter on that platform, but would not allow your binary to run on any older platforms. So really what we want here is the best of both worlds, which you can't get by doing purely compile time choices. We need to do runtime detection instead. And so GCC, our compiler, has a feature called multifunction versioning, which is quite slick. And it allows you to take a function that may use GCC intrinsics and tag it for the various architectures that you would like it to compile for, ranging from Core i7 to something that supports AVX 512 or whatever it may be. And then when you compile your binary using this, GCC will compile multiple versions of that function, one for each of the target architectures that you've specified. And it will then, as your application starts up, do a runtime check against the CPU ID, figure out what you're running on, and patch itself, put in the correct version of that function. And so SPDK has one place where we already do this to make it portable, but the challenge here is that our dependencies will also need this. So we need to finish off any places in SPDK that use intrinsics and tag things like this, but we also need to deal with our dependencies, particularly DPDK. And we need to make DPDK do all runtime detection for many of these things. And the only way that's really going to make progress is if we write a lot of tests. And the tests are mostly running, our existing tests inside of virtual machines emulating different target environments. So that's one of the challenges going forward for cloud natives. We need to do runtime detection of CPU features. Another thing we need to keep working on is interrupt mode. I talked a little bit about this before, where now we are able to shift lightweight threads over to single reactors, to single P threads, but we can't put that remaining P thread to sleep, even if all the lightweight threads on that one happen to be idle. So there is work ongoing on this, but it is a considerable amount of work, and we likely need community help to get it entirely finished. The strategy here is that every polar registered on a lightweight thread must be associated with a file descriptor. And if we switch a lightweight thread into interrupt mode, that file descriptor becomes, we block on that file descriptor using epoll or some mechanism like that, so that we can be woken up when there is an event rather than polling it. And so in order to switch to full interrupt mode, every single poller in the entire code base has to be mapped to a file descriptor that becomes readable when there is work to do. And only once that is done can we switch a lightweight thread into full interrupt mode. So there's a lot of work here. It could have a big payoff. This is what would get us to, when you're idle, the CPU use actually goes to 0 instead of just going down to 1 core as it does now. I believe this to remain critically important. I think the work will be done piecemeal. And the most important or most commonly used, it's probably the correct way to say that, pollers will be done first. And if you happen to only be using those, then it will drop to interrupt mode right away. There will likely be some straggler beta modules or something that spawn pollers where it's difficult to build a file descriptor that becomes readable when there is an event, and those may take a significant amount of time. So, and then we also need to explore alternatives to epoll, things like umonitor or umwait to put CPUs into low power states without necessarily releasing our time slice or making a system call, because this would allow us to wake back up much more quickly. Okay, so another really awesome area of work that is happening right now and needs to continue into the future is to improve what we call our thread scheduling algorithms. And so I'd mentioned that now we can move lightweight threads around onto different P threads in different reactors. And so then the question becomes, when do you move them? What's the decision-making process, right? And so we've added in the latest SPDK release a plugin system for making these thread movement decisions. The default static scheduler is round robin distribute the lightweight threads onto the P threads as they're created, which is what SPDK has historically done. There is now a dynamic scheduler, which is trying to measure how busy each thread is when we poll it, and collapse them down onto a smaller number of P threads to save power. But there's a lot of work here to figure out what the best approach really is. And so I think critically, we need to shift our benchmarking away from raw IOPS or latency to measuring things like IOPS per watt. And so fortunately, a lot of the newer server platforms report power draw directly, so you don't need special equipment to analyze power anymore. So these metrics are relatively easy to produce. What's difficult is determining exactly how busy a core is from the feedback we get, which is mostly, did I find any events when I polled? And that's the fundamental piece of information that we have. There's a lot of really cool ideas here, measuring the branch prediction hit and miss rate to determine if a thread found interesting work to do. If it misses a bunch of branches, it probably found new things to work on. But there's probably just simpler metrics of trying to map the percentage of time that a thread has reported that it found something versus not onto a % busy. And those are likely not a linear relationship. It will find things to do, much more frequently than what we would consider it as the same % busy. It's probably more toward the idle side, even if it's finding something to do 50% of the time. And then another thing we can do is integrate with a feature called Speed Step, which is on some of the newer Intel platforms where user space code can control the CPU governor. And we can deal with these sort of in-between cases where you may have a P thread that is running one lightweight thread, and you determine this is like half or a little bit more than half busy, and you've got another P thread that is running a lightweight thread that is like 20% busy, and or 30% busy, and So then you shift it over and you have now one pthread that's like 80% busy. Well, you're not going to really be able to shift another lightweight thread over to that pthread without going over and bottlenecking. But you're not really 100% busy either. So what we can do in those cases is just gradually downclock the CPU to save power until it's closer to 100% utilized. So those are some of the ideas that we have. I'm sure there will be lots of clever ideas in the future about how to save power and to be more efficient in these poll mode systems. We're also going to need clearly new mechanisms to get IO into or out of both virtual machines and containers. And so I'll start with the container case. Today, shuttling an IO from one container to another on the same system requires 2 data copies in most cases. This is a common case, it turns out, for a lot of these storage services. They're deployed as a sidecar container or a daemon set container in Kubernetes, and they're providing some storage service, and the other application containers are connecting to them. And they happen to be running on the same node or in the same pod even. And so they're just shipping, read and write commands back and forth between the 2 containers on the same system. And from what we've measured today, the fastest solution seems to be to use the NVMe over Fabrics driver with TCP from the Linux kernel to connect back to an NVMe over Fabrics target running in the storage service container with SPDK. But that's doing at least 2 data copies, one into the kernel block stack, and then one back up to SPDK. There must be ways to do this more efficiently. This memory is all in the same system. They're all in the same node. There have to be ways for us to either offload this or to avoid data copies. And so that's one area where we need to look for improvements. The other thing is there is a new protocol for virtualization, virtualized NVMe devices. And in fact, there's a whole talk about it coming up later that I will give part of. This new protocol is called VFIO user, and it allows us to finally present fully emulated NVMe devices to virtual machines instead of using, for instance, VirtIO block or VirtIO SCSI as we would have historically. And so this protocol, it's still shared memory based like VirtIO SCSI or VirtIO block, but it is talking NVMe and it's using regular NVMe drivers in the virtual machine, and we expect it to be considerably faster. So we need to get this over the finish line. QEMU support is well on its way, and standardization of the new protocol is well on its way. We're really close to the end here on that. We also need to consider other VMMs that may want to support VFIO user, and there are a number of other ones, especially the lightweight virtual machines. Okay, and so then a couple of other longer term ideas to finish out the talk, and hopefully I inspire some people to join in and contribute some of these things. One idea is that we could do a cloud native ENV layer in SPDK. So we have a pluggable environment abstraction layer today that is based on DPDK. And this layer is in charge of allocating DMA safe memory, enumerating the PCI bus, low-level operations like that. And so we could do an ENV layer that is just not capable of allocating DMA safe memory. And if you try, it fails. And so this would restrict the feature set that SPDK has. We would not be able to run user space drivers in this. But we could still do a lot of what SPDK does. For instance, the entire NVMe over Fabrics target, if you're talking to a backend device that is also over the network or is in the kernel and you're using IOU ring or libIO to talk to it, this doesn't need any user space drivers. And I think there's probably still value in that. This also allows SPDK to run without huge pages. Now, huge pages help performance, and they're required to do DMA, but we do not necessarily have to have them if we're doing no DMAs. And so that while all of the cloud providers today do allow ways to configure huge pages for containers in the cloud, this would make it easier. And it also eliminates our DPDK dependency, just because DPDK is only used through the env layer. So if anybody is interested in working on that, you work for a cloud services company or something and think this is interesting, certainly we're interested. And then I'll finish it off with a fun one, because Rust is all the rage these days. Certainly, I think it would make sense for SPDK to think about integration with some of the more popular languages that get used in the cloud. The two big ones are of course, Go and Rust. Go already has a fairly good story for SPDK in the control plane. I don't think integrating SPDK with Go in the data plane is necessarily something people are going to want to do. But from the control plane, we've already chosen JSON-RPC as our control plane interface, and Go has excellent support for that. So lots of people are managing SPDK applications today using Go. I think that's already a good story. But Rust is definitely a target for data plane. And so people are going to want to use this. In particular, I think they'll want to write BDEV modules in Rust, and that they'll probably want to use SPDK, maybe just the NVMe driver, but maybe more from a Rust application. And that involves packaging SPDK as a Rust crate. So there's been some attempts, if you look at the code for MyStore that's written in Rust, uses SPDK. There's been some challenges already identified. I'm sure there will be more as more people attempt to do this. But I just listed some of them here, which are a little interesting. The Rust linker doesn't support C constructors, which we rely on. Missing a couple C APIs for things that we do have JSON-RPC for, makes it challenging. And then the bindings for SPDK, SPDK is a low-level C library. It's not simple. It's as simple as we can possibly make it, but it is still a low-level C library designed primarily for performance. And so some of the binding generators get tripped up. There are void pointers, for instance, in the SPDK interfaces that maybe type defs would help the binding generators sort out which void pointer is actually the same as another void pointer, things like that. And then there's probably some benefit to handwriting the bindings to make them more ergonomic for Rust. So with that, I'd like to thank you all for listening, and we can go over to Q&A.